This video covers torque. Now we've seen torque before. It's represented by a tau. It is the tendency of a force to rotate an object about an axis. Now, torque is a cross product of R cross F. Now, R is a lever arm, and it is the distance from the pivot point to the location where the force acts. Now, we've seen a dot product before, where work is the dot product of R and F, and we said that these two components needed to be parallel to each other, or wanted to be parallel to each other. This cross product tells us that R and F want to actually be perpendicular to each other. So R cross F translates to RF sine theta. Now, just like in work, it's going to be very important that you understand what angle you need to put into this particular theta. Torque is analogous to force. What that means is if you think back to Newton's second law, which is the sum of the forces is equal to mass times acceleration, this tells us that if we have an unbalanced force, we're going to have linear acceleration. Well, when we say a torque is analogous to force, that means if we have torques or unbalanced torques, we're actually going to have angular accelerations, but we'll see this again in a little bit. Now, the most important thing is going to be that force and R are perpendicular to each other. So in this example, we have a force being applied at an angle. Well, the component of force that is perpendicular to R would be F sine theta. So R times F sine theta will produce a torque. So these are three of the most common examples. If we have a force that's being applied like in this first situation, then the angle between R and F is 0. And we can see that the sine of 0 is 0. So there will be no torque produced or no rotation produced. The greatest torque is going to be provided when you have a force that is perpendicular to R. Again, when your theta is equal to 90, because the sine of 90 will be equal to 1. And so your equation reduces down to torque is equal to R times F. Now, if you have a force that is applied at an angle, then you can use theta as your angle, carefully, and torque is equal to RF sine theta. Now remember that torque is made up of R times F, and R is measured in meters, F is measured in newtons, so torque will be measured in Newton meters. Now, just like we saw in rotational kinematics, anything that is clockwise will be negative, anything that is counterclockwise will be positive. So if a force produces a counterclockwise rotation, then the torque produced is also positive. So here, what you're seeing are forces causing counterclockwise rotation, so positive torques. Here, you see our forces are causing clockwise rotation, so they produce negative torques. Now think about a circle with its axis of rotation in the center, and we are applying a force a distance r away from our axis of rotation. Now, if we look at this force, it's going to cause a clockwise rotation, or a negative torque. If we apply a force here, also a distance r from our axis of rotation, this is going to cause a counterclockwise torque, or a positive torque. Now, if these two forces are applied and this object does not rotate, what we're saying is that our sum of our torques is equal to 0. And this situation is known as static equilibrium. So if that's true, that means all of our positive torques plus all of our negative torques is equal to 0, or our counterclockwise torques are equal to the sum of our clockwise torques. What that means is if you look at this example, we have a 3 kilogram box 1 meter away from our axis of rotation, in this case our fulcrum, which is this triangle right here. It's our axis of rotation. And we have a 2 kilogram box some distance away from, again, our axis of rotation. Now, if we want this seesaw to be balanced, then the sum of the torques needs to be equal to 0, or the sum of the counterclockwise torques needs to be equal to the sum of the clockwise torques. In this case, on the left-hand side, the force that's causing rotation is going to be mass times gravity. And again, multiplied by a distance r away from our axis of rotation. On the right-hand side, our 2 kilogram mass will also experience a mass times gravity. Again, some distance r away from my axis of rotation. So again, if I want this entire system to be in equilibrium, then we need these two quantities to be equal to each other. Or to say that our 2 kilogram mass is 1.5 meters away from my axis of rotation. Now our last situation assumed that the plank that these two masses were sitting on was massless. But if that plank is not massless, meaning it does have mass, then we can actually calculate the center of mass of that plank. And if it's a uniform mass, then the center of mass will be located right in the middle at a distance L divided by 2. That means if we still want our whole system to be in equilibrium, that means causing no rotation, we need to take into account the force that's going to be acting on the center of mass, which is still mass times gravity, but now it has to be included. So down here at the bottom, we have the mass of one object times gravity times its distance away from the axis of rotation is going to be equal to the mass times gravity of my second object, plus the mass times gravity acting on the center of mass. Now for these situations, you just need to make sure that you read whether or not whether the plank that these two objects are sitting on is going to be considered massless or not. Now something we've been hinting at the entire time is that if torque is analogous to force, well then the sum of the force, which is equal to mass times the linear acceleration, is going to have a rotational component too. In this case, the sum of the torques is equal to moment of inertia times angular acceleration. Again, you want to think of everything in linear quantities translated over to rotational quantities. So again, we said that force is going to be very similar to torque. Moment of inertia, again, inertia is a measure of its mass, is how we rewrite mass, and angular acceleration is the translated version of linear acceleration. So this situation will only be used if an object is not in equilibrium, meaning that the forces applied will cause acceleration, angular acceleration to be more specific. So since this example is entirely something you've never seen before, you're going to need to include it for full credit in your notes. Consider a beam of length L, mass m, and a moment of inertia about the center of mass 1/12 ml squared. It is pinned to a hinge on one end. Determine the beam's angular acceleration. So just like in forces, we're going to start off with a free body diagram and label all of the forces acting on this beam. If it's a beam of length L, mass m, that means our center of mass will be located right in the middle. And on this center of mass is where gravity will act. Now we do have a couple of other forces acting on this beam, coming from the hinge. So the hinge is providing vertical forces and horizontal forces at all times. But because these forces are located a distance of 0 away from the rod, they don't actually provide any torques. So this mg is the only thing that's providing torque or causing rotation. So the first thing we want to do is find out the component of mg that is perpendicular to r. So if we look at this problem like an incline, we can see that mg can be broken down into components. And this component that's going to be perpendicular to the lever arm is going to be mg cosine theta. Now this theta right here is the same theta given to us in the problem. So that's convenient. Now this r, the distance away from my axis of rotation, is going to be equal to L divided by 2, the length of the rod divided by 2. So the sum of our torques is equal to the moment of inertia times the angular acceleration. So RF sine theta is equal to I alpha, and R is L divided by 2, F is mg cosine theta, and the angle between L divided by 2 and mg cosine theta is 90 degrees. They're already perpendicular, so this piece becomes unnecessary, equal to I alpha. Now again, what we're trying to do is solve for your angular acceleration. But the problem is, before we do that, is this moment of inertia. Now we know that a moment of inertia is mr squared, where r is a distance away from your axis of rotation. But the problem is that the moment of inertia that we're given is about the center of mass. But we're not rotating about the center of mass. We're rotating about one end. So what we can do is actually use the parallel axis theorem, which is the moment of inertia about the center of mass plus the mass, total mass, times the distance that the axis of rotation has moved from the center of mass. In this case, we're given 112 ml squared as our moment of inertia about the center of mass. The total mass is m, and the distance that the axis of rotation has been moved is L divided by 2. L divided by 2, mg cosine theta is equal to 1/12 ml squared plus ml divided by 2 squared times alpha. Now if we simplify this right-hand side, we get 1/12 ml squared plus ml squared over 4. Finding a common denominator, we get 4/12 ml squared, or 1/3 ml squared. That simplifies down to, and again, here we're trying to solve for our angular acceleration. One of our L's is going to cancel out, the masses will cancel out, and we're left with 3/2 g L cosine theta is equal to our angular acceleration.